There we go. Let's get the sound on. Good start. So, good morning. It's about what 9:30 in the morning here in the UK, and this is my new attempt at a live stream. So I've been really wanting to do this for a little while, and I'm really excited about having the opportunity to do something a little bit different. So I'm basically having a bit of trouble finding time to make videos right now. I'm really busy. And one of the things is that I think my approach could be streamlined a little bit. So I'd really like to just start working on things and edit the results down just by capturing everything that I record in a session. And so I think with these kind of live videos, my edited, properly recorded, released videos on my channel, they take a fair amount of work to do, but I try and put quite a lot of effort into them because I want to make them good. But some of the time it just feels a little bit overly heavyweight, a little bit overly formal for some of the things I want to work on. And also you can't always tell whether what you're working on is going to be amazingly interesting or not up front before you do it. So I think if I start doing all these live streams, we'll get some interesting results and you can follow along. Now, I think my subscriber count to this stream right now is pretty low. I think I've got 1 subscriber, but everything has humble beginnings, like this whole channel. And the thing is that you've always got to start somewhere. So, if you're here, if you're watching, join in, log into the chat. I've got a Gitter chat you can see in the overlay down the left here. Now, just before we get started, let me just give you a little quick tour of the streaming setup that I've got here. So I've got my webcam here, obviously, and I've got the chat for you to talk to me. I've got my camera mounted up on the camera arm here, and we can have a look at the project. And while we've got that, we've also got my wide camera in the top left, and we've also got the webcam, so you can see and speak to me, and I can see you. And also we have the desktop recording, so I can shove things up on the desktop, things that I'm working on. I can do a split screen, picture in picture between the two. I've got the Eakins microscope hooked up, and I'm using the Lenkeng HDMI capture device, so that little HDMI capture device keeps coming around and it keeps coming in handy. And then I also have a CCTV camera pointed at the 3D printer for when I do a little bit of 3D printing. So I've got a little setup here. I think it could be improved, but I think it's going to be a nice little start, a place to begin with recording things here. So let me just do a little bit of a catch up. So some of you might have seen my previous video about this little device over here. So this, let's get this moved over a bit. How's that? There we go. So this thing is this software-defined radio that I was working on a number of months ago before I had to move out of the US, and obviously that move has taken up quite a lot of my time, and it's taken up quite a while to get back to this project, but I haven't forgotten about it. It's been something that I've been chipping away at in the background, and something that it's good to be back having a look at again today. Now, for those of you who didn't see the video, what I'll just do a quick recap about what we have here. So we have a couple of quite high-speed analog to digital and digital to analog boards here. So these two little boards allow us to play out some analog data or to capture in some analog data. And then at the heart of this, we have the Lattice ICE40 FPGA, which is the first FPGA ever to have a completely open source toolchain. Now, the ICE40 has been something that I'm really interested in this channel. It's very exciting to have something like that available. You know, trying to do two things at once. Get the exposure right and explain what's going on. So the Ice 40 is exciting because thanks to the work mostly of Clifford Wolf and several other people, this FPGA is the first ever FPGA to have a completely open source toolchain. And what that means is that previously the tools that were available for synthesizing firmware for these FPGAs were incredibly cumbersome. They're huge downloads, they're not being particularly actively developed, and there is a real problem with the ecosystem of tools that's available for FPGA technology. Now, this is a problem that is rapidly changing, mostly due to the work of Clifford Wolf and other guys who are working for Symbiotic, which is a small startup, and various other open source contributors who are chipping in. So I think we're going to see quite an exciting time coming soon, where we're going to see a great improvement in the ecosystem of tools that's available. So I kind of liken it to the arrival of the compilers that we have in the software space, like GCC and LLVM. So previously, the compilers that were available were highly proprietary and locked down, and they did the job well enough in order to sell compilers to people who wanted to use them and sell the chips, but they were never spectacular because there was never any commercial need for them to be developed beyond a certain point and for companies to invest beyond a certain point. And this is where the open source approach to things really comes into its own, because people can work on a project just for to scratch their own itch, because they need to make an improvement that might not be necessarily of any interest to the original manufacturer of the software. So I think what we're going to see is a massive improvement in the accessibility of FPGA tool chains, and I think it's really going to cause FPGA technology to take off among people who are doing it more for fun, or people who are doing more creative projects, because previously there was a very, very nasty high barrier to entry with FPGA technology. And as of the last few months, it's not just the Ice 40 that's available with an open source chain, the tool chain. The tool chain is now broadening out, so there are more FPGAs becoming available. There's work going on to make the ECP5 have a toolchain similar to iStorm toolchain, and there's also work to get the Arctic 7s and the Spartan 7 series going in that manner as well. So I think we're going to see some really exciting developments going on with the FPGA tools. And one of my sort of focuses on this channel is just to really make those tools more open for people to use, because I think a lot of the people working on it are engineers, and I really want to promote their work and make sure more people feel comfortable using it. So for that purpose, I built this little software-defined radio rig. It's nothing too much. Basically, it consists of those two DA A to D, D to A boards, as I mentioned, and then I've got these little ribbon cables here, and these connect it together onto the Ice 40 over here, which is the FPGA, of course. And then the FPGA is now, well, was previously, when I first made this video, it was plugged into a Raspberry Pi underneath, and the Raspberry Pi has now been replaced by this little board here. This is the ICO US baseboard. So the ICO US baseboard is designed so you can plug the FPGA into your PC. So this is an FT2232H, which is a USB interface controller. And so the idea here is that the Raspberry Pi was good to get this rig up and going, but I don't really want this thing, this whole rig, to run as an independent device, as a separate computer in effect. I'd actually like it to work as a peripheral for my PC. And my plan here is to set up some firmware for the FPGA that will stream the data in through the analog to digital inputs and allow you to capture it through USB into the PC, and also do the reverse to play data out of the PC and out of the digital to analog. So we can use this for all kinds of software-defined radio projects. Now, my plan here is to then take care of the software side on the PC, and then make it so that we can stream the data into and out of GNU Radio. Now, GNU Radio, you probably might have heard of it. is a suite of tools for doing digital signal processing and radio communications. So a lot of the work in terms of making a software-defined radio can be taken care of by the tools that are already available from GNU Radio. So what I'm going to do today is I've got a few hardware problems to solve, and we'll see how far we get with that, and then I'm going to see how if I can chip away at the software problem a bit further. So we'll see how we go. I'm going to work on it for maybe an hour or two, see how we do. If I get stuck, I'll probably stop and then come back another time. And also, of course, as you know, this is my first stream. I'm really happy to be here, but we'll see if anything goes wrong, if the audio fails, or if we get some technical difficulty. In that case, we might have to break off and try another time. But let me know how you think things are going. Jump in the chat if anything's going wrong, or if you have an opinion about what's going on. And I'm having a great time, and hopefully you all will too. And also, if you're coming in watching the VODs later, welcome, and maybe I'll catch you next time live. But of course, I am actually streaming at quite a weird time, so this is in the morning in the UK. I'm in control of my hours, which is quite nice, but I think maybe the whole American audience will come and watch the video on demand later on. But this is a good time for me, and if I have a good time for me, then it's a good time for me to stream. So let's get started. So to begin with, I need to pull up my big table. Okay, and I also need to download the FT. So I'm going to download the FT2232H manual. So that's that USB interface controller on the ICO US baseboard. So let's pull that over here. So this little chip, you probably might have seen these before, but I'll just go through them a little bit for people who haven't seen these. These are basically quite flexible peripheral chips for you to attach your project to a PC, and you find these in all kinds of different devices, and they're useful because they have a variety of different modes, and so they can interface into different types of device quite conveniently. So at the heart of it, they've got this USB protocol engine, and then they have these two channels of the MPSSE, multi-purpose serial interface that these things have. And so as we scroll down, you can see in the index there's a whole load of information here. And then in this table here, you can see the pin mapping on the device. So depending on the mode you have the port, channel A and channel B connected into, it can act as a serial port, RS-232, as different kinds of FIFO. It can do bit banging, it can do synchronous and asynchronous, which is, you know, whether the clock is being generated or provided externally. It has this CPU style interface, which allows it to the FT22 to act as a memory device, and all these different modes. But for my use, I want to have a synchronous FIFO, which will basically mean that we're going to be sending data streaming from the FPGA, and there's also some flow control involved in this. So the FPGA isn't going to always be ready to receive data. We're going to have a bit of buffering in the FPGA, which is going to fill up and drain out, and equally sending traffic from the PC to the device. There's going to be a little bit of ebb and flow in terms of the data that's being sent. So there's quite a lot of flow control here, where the FT2232H device indicates that it has data to receive, and the FPGA can indicate that it has data to send, and so on. And then we have an 8-bit data bus. The FT2232 provides a clock, and then this OE thing is for the FPGA to indicate that it has data. So let's just go down, and somewhere down here there is the timing diagram. Let's see if I can find it. The index. There we go. So, nope, that's the pin out again. There's a timing diagram somewhere in here which I really want to find because it's very, very helpful. Where'd it go? There we go. Okay, so yeah, you can see how a read transaction works and a write transaction. So what's going to happen here is the FT2232H is going to generate this clock out signal, and this clock will drive the FPGA, and the FPGA will use this to keep synchronized with the bus for the FT2232. And then when there is data to receive from the PC, the buffer inside the FT2232H will fill up, and it will assert this RxF line, drive it low. And when that happens, the FPGA doesn't have to immediately respond. It can wait until it's actually ready to receive the data. So the first thing it's going to do is assert this output enable line, and this basically this is the FPGA saying to the FT2232H, you can now drive data onto the data bus. And this is a way of the FPGA and the USB controller making sure that they don't end up both trying to drive the bus against each other, both fighting each other. And so what's going to happen here is once the FPGA gets that notification, there's data to receive, it says, okay, you can drive the bus now by asserting this OE thing. And once that's done, it then later asserts this RD hash line, which basically says now start reading data. And then the data changes on the rising edge of the clock, and it's read by the FPGA on the falling edge. And then the write transaction is a little bit simpler, because by default, when the OE line is high, then it's the FPGA's turn to drive the output bus. And so when the line is driven low, TXE, by the FT2232, this is basically saying the transmit buffer is empty enough to receive some data from the FPGA, and so it will keep that low while it's got room for more data to receive. And when the FPGA actually wants to go ahead and send some data, it will do that by asserting this WR line, and then once that WR line is asserted, then the FPGA writes those bytes onto the bus. So the protocol's reasonably simple. Now the problem that I have here is that the ICO board was not really designed for this use case, and I think the purpose of the ICO US baseboard was mostly to act for some RS-232 type applications and enough interfacing to be able to write firmware into the FPGA, but it wasn't really designed to be a high-speed data interface into the PC. So one of the things I've been doing is tracing with this table the mapping of the pins that we need all the way from the FT2232 all the way through the ICO US baseboard to the pins that are on the header that are attached to the that the ICO US baseboard attaches to, and then on the other side how those pins are then mapped through to the FPGA. And if we have a look at it, if I sort this, let's sort it by name here. All the green ones that I have here are the data lines, and they all map through to FPGA pins nicely, and all the all the yellow ones are control pins, and they all map through to the FPGA pins quite nicely, except for this one pin, RxF, which is really unfortunate. So all the interface is there apart from this one pin. Now it's a while since I did this spreadsheet, so I just want to go ahead and double check that. So let me just let's pull that up. There's a data sheet somewhere. In fact, it might even be in my folder. No, I think it's here. Downloads. Schematics. Woohoo! There we go. Okay, so there's not much to this. Get rid of the sidebar. So here is the FT2232, and in our case the RXF line is AC bus 0. AC bus 0 is mapped through to, it says it has a line, that's good. See if we can find this. Now, have I got myself a bit confused here? Don't think so. I did check this quite carefully, but it's always better to just check things multiple times just in case you make a mistake or whatever. Now, one thing that I'm also noticing, that I highlighted the clock out line here in red, and that is also a problem because you can see that it's crossed off here. So I think what we're going to do with that is do a bit of soldering, a bit of modification to get this up on the header. So I think I highlighted that one previously just to indicate that we could modify the ICO US baseboard in order to get that AC bus 5 routed through for the clock out. So we really need that one. And the RXF line is also going to be necessary if we want the PC to be able to send data out. So it's not totally necessary if we only want to make a software-defined radio that can receive data, but it would be very, very helpful in terms of sending data. So let me just have a bit more of a trace through, just see what we're doing here. Okay. Right, so there's my problem immediately, is that, well, AC bus 0 goes to GPIO 13. Huh. Wonder why I didn't spot that before. Now, there are some notes about this. AC bus 0, replace AC bus 0 from pin 33 to pin 27. So there are a few little board mods on the ICO US baseboard. So I wonder if those things are not going to be connected up in a way that we can use anymore. But that might be the case. Pin 27. Right, yes, that's a problem because pin 27 is this ID SDA, which I think is used on this board for. Is it used for identifying what the ICO board is? I don't think it goes directly through to the FPGA, so I'm just going to annotate that on my spreadsheet here. So the J8 pin is 27. ID SDA and so with Raspberry Pi, let's have a look at the pinout for Raspberry Pi. What does that end up being on the Raspberry Pi side? Right, yes, that's the problem. So this is the I2C ID EEPROM that the peripherals for the Raspberry Pi have. So yes, this is not a general purpose line. Now the other question is, what does the ICO board treat that as? Because obviously there's no Raspberry Pi involved here anymore. There's a schematic somewhere in here. Somewhere. There we go. Schematic. Oh, I always do that. I don't want to zoom the page, I want to zoom the Google PDF viewer. Makes a difference. Right, let's see if we can find the header on here. Here we go. Right, so this is on here, that pin 27 is ID SD. And while we're at it, pin 28. Ah, that's weird. Looks like I've got a duplicate row here. Now let me just check I haven't got any missing. Yeah, looks good. So what is it? Now if I remember, one of the problems is that on this board there is this support FPGA, a little Mac X05, and the issue we have is that some of the communication lines don't map through to the main FPGA. They map through to this little Mac X02, and this guy's job is to act as a little intermediary between the Raspberry Pi and the FPGA, and we might end up in problems if that ID thingy is being wired through to this. Although it doesn't look like it. So what does it go through to on the FPGA? Ah, this little EEPROM on the board is the where those signals are being routed through to. Okay, so that's a problem. That doesn't go through to the main ICE40 FPGA. So we're going to have to figure out an alternative method of getting that signal from the FT2232 through to the FPGA. So I'm just going to mark that off on here. So really both of those. Need marking off because they don't go anywhere. Okay, so yeah, so this one is a problem. So we're going to have to do something with this. And then when it comes to BD bus 5, now what does that actually entail in the FT2232? Is that anything that we really care about? No, fortunately, it is not. Okay, that's good. Now, when it comes to the ICO US baseboard, these changes are a bit tricky. So basically in this schematic, the schematic is the original version of the board that I have, and then it has these mod wires attached to it. And the description of what those mod wires do is described by this little piece of text here. So, change connection, add pin 27. Add what? What about it? Net AC bus 0 from pin 33 to pin 27. AC bus 0 on my chart goes to pin 27, yes. Pin 29, AC bus 7, now goes to AC bus 7 now goes to pin 28. Where's AC bus 7 on my diagram? Is that correct? AC bus 0 from pin 33 to 27. Yeah. And AC bus 5. What's that? That's on pin 36. Okay, and pin 33, BD bus. Not that we care about the BD bus. Okay, so if I'm not bamboozling myself here, and I'm hoping not to have done so, everything we need for this bus has been routed from the ICO US baseboard all the way through to the FPGA, apart from this RXF signal that's on pin 27. And the problem now is that I believe that this pin 27 may now actually be not connected to anything. Now, one of the nice things about the ICO US baseboard, which I was a bit puzzled by at the time, let's switch screens, the camera, is that it has an awful lot of redundancy in here. So I'm just gonna, just remembered I need to get this thing recording. Let's get the camera going. There we go. Okay, we'll be able to use those things for an edit later. So what we have here I'm just going to get some camera shots of the whole board because I'll need those for the edited version later. This is the problem with doing the stream for the first time, is you're trying to record a video at the same time as you're trying to talk to an audience. Oh. Huh. I was not expecting that. I can see you've lost the camera. So, that's an interesting thing that I didn't know. We're going to have to turn off the recording. That's okay. So basically the camera that I've got can't actually handle both streaming through the HDMI output and recording at the same time. So I can either give the stream to you or I can give the stream to my future viewers when I do the edit. And I think I'm going to give the stream to you because I can probably reuse the footage from the video on demand. So that's one little issue that we're going to have to resolve here. For future streams. Anyway, where was I? So, what was I saying? Yes, so when it comes to the ICO US baseboard, and this kind of puzzled me at the time, was that it just has all this redundancy here. So, there's really not much here. There's all this circuitry around here, the FT2232H, which is jammed into the corner. And then there's a load of these footprints which are just not populated. So these two 40 pin 0.1 inch headers here, there's nothing attached to them. And similarly, there seems to be the outline for a PMOD connector here, which similarly was just never wired up. So I don't know if the person who engineered this board thought that it would be nice to give the user a bit of flexibility in terms of what they have wired up so that they can just rewire this. And if they were thinking that, well, I'm the person who's coming along and taking advantage of that decision. It's very, very handy. So what we're going to do is make some modifications to this thing to try and see if we can get those signals that we need routed through. Now, question I have is what pin number, where does the signal actually get to on this board despite the modifications? So what we're going to do here is go back to the schematics. Now it comes to the FT22, so it's the pin 26. I might just add a little column here and just, it's nice to get all the information into the table. So, pin numbers all in there for everything. So AC bus 0, 16, 17, 18, 19, 21. You know what, this is going to screw up, isn't it? Let's take the auto filter off. There we go, right. $16, 17. Sorry, no. 26, 27, 28, 29, 30, 32, 33, 16, 17, 18, 19, 21, 22, 23, 24. Okay. Awesome. Right, so pin 26. And then exactly how many pins are on this package? Which package do I actually have? Let's Let's have a look and see if we can get the package markings off. It's a good excuse to use the microscope. There's quite a lag on that. Hold on. Just setting it up so I can see the results, because I've got my stream preview, but there's such a lag on it I can't use it in real time. Okay, there we go. Okay, let's bring that into focus. Okay. There we go. We'll boost this up a bit so get more of an overview. Okay, so this is the nice thing is that if we look at the microscope image, it's got the description of the package type that we've got, and it seems to be the -C package. Oh no, that's the revision number, beg your pardon. The H56Q, there we go. There we go. So this is the VQFN 56 package. No leads, hence the N. Quad flat pack. Very fine is the V. So on each side of this thing we have 56 divided by. Is it actually a square? Again, I just don't want to assume things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Good, it is. Great. Okay. Now my microscope's actually in reverse, so I'm just going to flip it round here. Okay, that's a lot better. Forward a bit so I can actually see what I've got here. So I need pin 26. So pin 26 is going to be, let's have a look, get back to the microscope, there we go. So 14 pins on a side, and the pin on the pin with the marking right here is going to be pin number 1, and then it's going to go around clockwise on this package here. Okay, I think we're going to need to unmount this from the frame because the frame's getting too cumbersome. Unmounted. Okay, so let's just get this unmounted from here. Okay, that is going to be so much more convenient. Right. Now I can actually get it under the microscope and fit it in here. Let's move this a bit higher so we can get a bit more. A bit more of an overview. Look, a little hair there. Get rid of that. Okay, a bit more light. Okay, now this is one of those things where it's super easy to lose complete count. You guys are not seeing the microscope camera, are you? Let me try and fix that for you. Oh, there we are. Yeah, it's working. Okay. This is definitely getting the old first stream teething problems, but so does it just lock up when I do that? We're gonna have to do something about that. And it comes back when I'm, so basically when I'm not looking at the preview, it seems to be locked up. Okay, we're gonna have to do something about that. We'll fix it for the next stream. But for now, what I can do is take a little screenshot of the view that I've got on my screen, and then we can load that up and then try and annotate, because I find it so super easy to just end up confusing myself and losing track of which pins are which when trying to make these kind of modifications. Okay, so this here is going to be one. We're about to have it in white. You know what, I don't want to use GIMP, I want to use Inkscape for this. So what I'm going to do is just annotate a few of these so I don't get confused. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, of course. And then this one will be, this one down here will be 28. And then the one we care about is 26. Right, so it's going to be, just double check that, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Right, so it's this one right here in the middle of this muck, like that right there. Okay, so the question is, what is that currently wired to? Let's get the microscope straight in. Looks like it goes around. So we're previously, in the previous version of the board, gone through to, which pin was it? AC bus 0, 26, AC bus 4, that's interesting. There's a bit of a disconnect between the pin numbers on this schematic and the ones I drew out of the data sheet, so I may have actually misread what I have here. Again, I know it's a bit tedious, but it's so important to double check these things because, well, as the old saying goes, you want to measure once, measure twice, cut once. AC. Yeah, I mean that's... Oh, I see. So this is the pin out on the 64 pin version, which is not what we have. We have... Well, it's not listed, but... It's not listed on this table anyway. Okay, so we're just going to have to... I think we'll just take the version that's on this schematic here, take the pin numbers, lock that on top, because they're obviously different on the 26 pin version. Okay, 12, 13, 14, 15, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28. Okay. Right, so we care about that. It's that pin 22. So that's going to change what we've got on this little diagram here. So that might be good for us. It might be a bit more accessible. Oops. So 15, 16, 17, 18, 19, 20, 21, 22. Straight into a via hole at the bottom here. Okay. Right, so where did that used to go on the schematic? AC bus 0. Used to go to those pin headers. Okay. I'm going to want to, I think I'm going to want to confirm that by buzzing it out. Let me get my multimeter. So it goes off to that one of the pins on that 40 pin header, and I believe, yeah, I can see where that mounts to. Okay, so that's going to be quite that's going to be quite nice for us. So let me just pull that over on the screen so you can see it. Where are we going? So it's a bit laggy. It takes me a minute. Okay. So what they've done here is that next to the pins on the unpopulated 40 pin header, the 40 pin header seems to be in the middle of between the FT2232H and the Raspberry Pi header that goes through to the ICO board. And then in between the two, there are all these 0 ohm links here, linking them together. And obviously they had some problem with the mapping of the pin they chose for this AC bus 0 pin. So they've taken the 0 ohm link here and removed it, which is fine because I don't need that. So what we can do is that over on this side of the board here, on the right, we've got this unpopulated header, 12-way header, just over in the middle here for a PMOD peripheral, and those are completely unconnected. So what we can do is just take that pin and connect it through to the PMOD header. So this is actually a really simple mod. I was worried that I was going to have to modify the solder little Kynar wires onto the FT2232H, which, you know, we can do. It's not a problem, but it would have been seriously fiddly. Whereas with this, all I need to do is put a header onto the board and make sure that I get that mod wired from the unpopulated 40 pin header through to the PMOD connector. Right, so next I want to figure out which pin of the PMOD connector is desirable. So for that, let's have a look at the PMOD standard interface specification. That's what I want. So this would be a Type 2A expanded one. And okay, we can just use pins 1, 2, 3, and 4 are signal, 5 and 6 power, 7, 8, 9, 10 are signal, and 11 is power. So what we can do here is just connect that pin that we want through to pin 1. So let's just fire up the old soldering iron. Give that a minute while it warms up. So what we can do is mount this header on here, and so this is going to sit directly underneath the ICO board, and then we can just use some jumper wires to jump to the one of the PMOD connectors on the ICO board, and it's not too bad. It would be really nice if we could get this signal through the Raspberry Pi header, but I was looking at it a few weeks ago and I just don't think there's anything left on the Raspberry Pi header that's available. I mean, there's 1 or 2 pins, but they don't go directly through to the ICE40 FPGA, and so you know the end result's not going to be that good. We'd have to modify the ICO board, which is going to be even harder to mod than this. So I think this seems to be the easiest way forward. So we're just going to do a simple mod. And so there's pin 1, so we need about this much length. Where's my solder gone? Now, when the US office closed of my former company, they had to get rid of a whole load of equipment, and I was the only engineer left. And they had a whole lab set up, mostly for optics, but also for electronics. And they sold off a lot of the more expensive equipment that they had, things that they could find a buyer for. But an awful lot of things were just not worth trying to sell. So they just said I could have them, which was nice. And at the time I had a Chinese soldering iron. I always like buying cheap Chinese things, see if there's something that can be made to work, of course, but it is also really nice having quality items. And this soldering iron is an Oki brand soldering iron. It's not too bad, and it's a significant upgrade from my Chinese one that I had previously. And crucially, the Chinese one wouldn't have worked with British 240 volts. Didn't have that ability, unfortunately, and so it's nice having a soldering iron that's nice and that I can use. I used to have one for British Power, but I think I got rid of it. Okay, so that's looking extremely promising. One of those ones where to make sure we get the first couple of pins in straight, so we'll just tack that in place. Blob. And then thereafter nice and straight. Let's go through and the rest of these all solder in place, because they might come in useful later, of course. I know it's the pin mapping. It's like, feels like the dumbest thing, just getting a set of pins from one chip, one board, one connector, one header, one schematic, through to another board, header, schematic, chip, so on. And it's the simplest thing, but it's so easy, especially when one schematic has been modified. It's so easy just to get yourself really confused. And so I've got this kind of slight sense of anxiety right now that I've got it wrong. But at least what I found out today doesn't seem to be in too much disagreement with what I put in the spreadsheet previously. So that's good. Okay, so this is looking pretty good. So now, like I was saying, this board, I can screw it back into this, and then the ICO board will slot back on top, like so, and then we can just use a little jumper wire to connect the two together down here. So let's get that mounted back up. I'm really excited about this whole streaming thing. Obviously this is the first ever stream, so we have one or two teething issues, but according to the dashboard I've got 3 viewers, and I think one of them is me. But if you're one of the other 2 guys out there, welcome. I'm really glad you could be watching this. I'm having a lot of fun doing it. I'm hoping it will, like I was saying earlier, I'm hoping that it will improve my workflow for video creation and also just allow me to put more stuff out there rather than just waiting for something that's really cinematic, really big and important, worth making an edited video about. Sometimes things are worth just sharing more informally. And then it's really cool, like playing around with OBS and getting those streams there. I mean, sometimes you just have to step back and think about what an amazing technological age we live in, that you know, we can stream and speak to people from around the world. And someone said it's like YouTube is like the Gutenberg press. Like, it's never been possible to, you can put your written word out there for hundreds of years, but putting your own voice and yourself out there is pretty new. You know, the idea that anybody can do it is pretty awesome. Okay, so here we go. So that's kind of what I said, right? That we have these two boards now stacked on top of each other. So now we can just jump between them. So I'm just going to have a rummage in my bag of wires. Now, if you don't have a few of these, they're well worth ordering. You can get them really cheaply from China. They're always sold under the name. I think you can buy them when they're called jumper wires, but you can get ones that are male both ends, female to male, and so on. But yeah, I mean, on AliExpress, they're always sold as DuPont wires. I don't know why they use DuPont. Is that in reference to the multinational chemical company DuPont? I don't know, but I don't know really. I mean, did they once make the plastic that was used in these wires? I don't know. I don't know why they're called DuPont wires, but anyway, according to this, I think that just needs to go through to the top one down here. So now we have sacrificed the PMOD connection on here, but we didn't need it, and now we've got that RXF signal routed through to the FPGA. Now I have no idea whether this is going to work, and the problem with this kind of project is that I've got to get my driver code to work on the PC side, not screw that up in any way, and make sure it's electrically working, and make sure the FPGA firmware is working, and they all have to work at the same time in order for this to work successfully. So we're going to find out whether I got that all working together, and I think it's just going to be a bit of back and forth trying to work out the details. Now, I have been doing a bit of work on the driver for that, and I've been using this board here as a stand-in. This is another FT32H board. I think I've got another one lying around here. You can get this one, I think this was an eBay one or an AliExpress one. It's worth having these boards just because the FT2232H is so flexible. You can use it for all kinds of things, and just having a nice little breakout board here can be rather useful. And these are really cheap, so I don't really care about breaking this thing, and it's also just a bit less cumbersome than the full FPGA rigs. So I think this is just a nice little stand-in that I've been using, a bit easier to use. So what I'm going to do here is try and get the data out of the FPGA, the ICE40, through the USB controller, and I want to send the data into GNU Radio, and I also want GNU Radio to be able to send data into this board. And so the idea is that then we'll be able to do lots of experiments with signal processing and things like that. So we need to write a piece of code, an FT2232H driver for USB, and then use the synchronous serial interface mode that the FT2232H has, and we'll be using that to send signals to and from the ICE40. I explained that a bit earlier in the stream. So I've been working on the driver code for this previously, and the way it works is that I'm using something called Soapy SDR. Now let me just pull up the website for Soapy SDR because it's quite a clever concept. Get my wires tangled here. It really does amaze me that I haven't lost more of my cables to running them over with the chair and getting them caught up in the wheels. Okay. Horrible thing to do to a cable. Anyway. Okay, where were we? Soapy SDR. Yes. Let's get rid of some of these things and get rid of the flicker. So that's another issue with my stream right now. Right. Here comes a Chinook going overhead. There's a Royal Air Force base near here. In fact, there's quite a few, so they tend to go overhead and make a big thumping noise. Anyway, so what is Soapy SDR? Soapy SDR is a C++ framework for drivers for software-defined radio devices. And the idea is to make, you can write a driver for Soapy SDR, and then your device becomes portable, not just to GNU Radio, but various other frameworks. And so you can make a single module that's interactive with a bunch of different things. Now, I really only care about GNU Radio, but from when I started with this, I got the impression that it would be a bit easier to write drivers for Soapy SDR than to write a custom GNU Radio driver, just on the basis that it seems like Soapy SDR just takes care of a lot of the boilerplate and common aspects of SDR drivers, and just reducing the amount of code I have to write. So I've been doing a little bit of work up until this point on the Soapy SDR driver, and my impression of Soapy SDR is sort of mixed. I think in terms of API design, it's alright. It's kind of simple. It's kind of old school approach to writing a framework. It's just reminds me of sort of 90s C++ approach to doing things. And of course, the downside of using C++ is it just makes your code a lot less portable. The main thing is that you define a driver for your device, and it's just your driver is just a derived class from this Soapy SDR device class, and so it's pretty simple to write. You just implement your own derived class. Of course, that could easily have been done in C. Using vtables, which would result in the same thing, and then it would have also resulted in code which is actually has binary portability, which would have been a nice thing. You know, there's not much that's one of the big sticking points of C++, is that between different compilers and different versions of those compilers, the ABI tends to change. So you can't just drop in a binary library that's written in C++ and mix and match different binary libraries between what they were compiled with. So C libraries tend to be more flexible in that way. So that's one reason why it just seems like a little bit of an odd choice to choose C++ for this application. But you know, I don't really care. This is all open source code, so it doesn't really matter if we can't have any binary compatibility, because we don't really need it. We can just recompile everything. So let me just let the cat in. There you go. This is Suki. Oh, I kind of want to show her because I heard all the good YouTube streams have cats, and this is Suki. She's rather sweet, isn't she? She's a little Burmese cat. She tends to come and stomp all over what I'm working on. Most cats do, but she's also quite sweet-natured. She doesn't mind being fobbed off and told to go away. She does like a bit of attention. The problem is if I get too much cat hair everywhere, it just gets all over everything. Anyway, okay, so let's see where we are with Soapy SDR. Yes, Suki. And drag this out to the right size so it fits the screen. I like using Tmux, and I think it's in 14 actually. So here's the source code of Soapy SDR, and there isn't too much to it. It has some example code here. The code of the framework, you can see it's just a few little source files here, all written in C++. I don't know, I get the vibe that this was a sort of something that was written by Windows type people, because they tend to use uppercase and lowercase in their file names a bit more. Just a little thought about that. Anyway, we've got this thing, the OTL modem, which is my code for a driver. So I'm just gonna, it's been a while since I've been working on this, so I'm just gonna get my little stand-in board here and plug it back to USB and just ensure that we can still talk to it. Got this Soapy SDR. So I've already compiled Soapy SDR and installed it just to save a bit of time here. And the main test tool is this Soapy SDR util tool, and its purpose is basically to just help you debug your device. So if I have a look at info. Yeah, that's info about this. Let's do a bit of probing. There we go. So I've got the driver that I wrote previously installed already, and it's found my driver and it's found my hardware, and it's found its information about it. So that worked great. The reason I'm kind of a bit, I don't want to say surprised by that, but basically I've been doing most of my work on this project on my personal account on this PC, and I tried to create a new account because I realized that I could end up leaking a lot of information, personal information, private information into the stream. So I've created a brand new account on my PC here just for the stream, just for you guys. The problem is that then you realize that everything that you need is in your other account. So anyway, it seems to be working. So here we go. So basically, let's have a little look at what the code contains here in the driver. So there isn't much here. In fact, there's one little source file, and this basically registers the driver class. So you write a plugin, and that might contain multiple drivers. and then when you've registered that plugin, it has the ability to scan for devices. So then inside here, in my device class, I'm using libUSB to do the actual communication with the device itself. And libUSB, sorry, not libUSB, well, I am using libUSB, but I'm using libftdi, which is a library for specifically talking to these FT2232Hs. So I don't even have to do the low-level USB implementation. That's all taken care of for me. And I've written a bit of initial code here. I think this is an old version, actually. Let's just stash these changes. You know, more things from a new account. Change my username. Where am I? Okay, so this repository just needs switching state because I've been doing some experimental work on the FPGA side of things, which I had uncommitted. Okay, so back to where we were. So in this code, we have this class that implements the device representative of the modem device, the SDR device, whatever you want to call it. And we basically support a range of sample rates. At the moment, there's only one sample rate that I'm supporting. So I'm really just trying to get to a simple hello world communication. So we use a libftdi to set up the stream coming out of the device, and then using the tool, using the test tool, we can just see about whether we can actually get data, any data in and out of the device. So let's see if we can just get that up and running again. This is now what I have to remember. We can just do that. You make the device. We put direction equals Rx, I think. Hold on a minute. Out of shot of the stream, I'm just going to secretly consult my history file in the other account, and then I can steal the commands that I was using. For Ropey SDR, rate 1 megahertz, receive. Okay, so it might not look like much, but you can see that with the little board that I've got here, it's receiving some data at a rate. Now, at the moment, because there's nothing hooked up to it, and this is the synchronous interface, there's nothing to drive this. So at the moment, the whole thing's just blocked up. There's going to be no data transferred. So the next thing is to try and get this attached to the FPGA and actually get some data coming out of the FPGA with this device. But I think for now, I think that's probably where I'm going to end it for this stream. But thank you very much for watching. I know things are a little bit ropey. It's all good trying something new like this. I think I've got a few things to sort out with the technology side of things. But yeah, this project's rapidly advancing, and hopefully we'll get to the point pretty soon where I can get some data out of the D2A converters into GNU Radio. So I'll be back with you very soon. Thank you very much for watching.